Hello, calculus fans. Let's suppose that we have a projectile that's fired with an angle of elevation alpha and initial velocity v naught, as in this picture. So you're shooting something from the origin, it follows the path of the red parabola, and it comes down and hits somewhere along the x-axis. The blue vector indicates the initial velocity that we're shooting this thing at. And let's assume that the only external force on the projectile is gravity. That is, we're ignoring air resistance and any other forces. Let's find the position function of the projectile, and let's find what value of alpha will maximize the range. That's the horizontal distance traveled. All right, let's place our coordinate axes like we had in the picture. The projectile is launched from the origin, and then the force, due to gravity, acts down. So, Newton's second law of motion tells us that force is equal to ma, which is negative m times g times j. G is the acceleration due to gravity. That's 9.8 meters per second squared. So, canceling out the m's, we can say that the acceleration is negative gj. Now we know that the derivative of the velocity is the acceleration. So, we can anti-differentiate our acceleration vector to get negative gtj plus c, an arbitrary vector c. Now we know that c is equal to v of 0, and that's v naught. That's our initial velocity vector, the vector at which we're launching the projectile initially. Now we know that r prime is equal to v, which is equal to negative gtj plus v naught. We're going to anti-differentiate one more time. Now we have r of t is equal to negative 1/2 gt squared j plus tv naught plus now a new constant of integration, which we'll call d. Now our initial position is 0. This is because we conveniently arranged it so that the coordinate axes had its origin at our launching point. So we're ready to write down our position vector of the projectile at any given time. It's r of t equals negative 1/2 gt squared j plus tv naught. So now let's say that the initial speed of the projectile is v naught without a vector symbol. And let's say that v naught can be decomposed into I and j components as v naught cosine alpha I plus v naught sine alpha j. Alpha is the initial launch angle of the object. So we have r of t is equal to minus 1/2 gt squared j plus tv naught. Now we're going to plug in the expression that we just wrote down for v naught. If we do that, then we get this. And what we'll do is distribute that t and combine like terms. So here's what we end up with. V naught cosine alpha t times I plus v naught sine alpha t minus 1/2 gt squared j. That's our position vector for the projectile. So here's another way of thinking about this. These values, x and y, are parametric equations for the position of the projectile. Now, let's say that d is the horizontal distance that's traveled. It's the x value when y is equal to 0. Let's plug in y equals 0 and solve for t. What we'll get is t is equal to 0, which we already knew. This is the starting point. And we'll also get t equals 2 v naught sine alpha all over g. We're getting this by taking this expression here, plugging in y equals 0, and solving for t. All right, you should work that out, see that you get the same thing. So let's use that second value of t, and let's plug that back into x to see what we get. All right, so our horizontal distance is an x distance. X was v naught cosine alpha times t, and then we've just worked out that t is 2 v naught sine alpha over g. Clean that up a little bit, we get v naught squared times 2 sine alpha cosine alpha all over g. And now you want to recognize this as a trig identity. 2 sine alpha cosine alpha is the same thing as sine 2 alpha. That's our double angle formula for sine. So the way we can make this largest is by choosing the value of alpha that makes sine 2 alpha largest. So that'll happen when sine 2 alpha is equal to 1. And that happens when alpha is equal to pi over 4. So we should launch with an angle of pi over 4 in order to get the maximum possible distance on the object. Okay, that's all for now.